my talk on the critical hydrogen content of high-strength steel wires. So, as a motivation, that's the technical background of our work. We have here so-called flexible risers, which are used in the offshore oil and gas industry. And there are several problems with hydrogen-induced stress corrosion cracking in the past 10 years. And so the most critical part of these flexible risers are the so-called tensile armor wires. And these tensile armor wires have to carry the whole dead weight of these flexible riser pipes. And what is the question from the industry is the material selection for these tensile armor wires and to improve the resistance against hydrogen embrittlement and also to have a material at a higher strength but also a good ductility and resistance. And therefore I come to the investigated material of my work. So it's a conventionally C65 carbon steel wire in 4 different modifications. You see on the left-hand side the hot rolled condition with the tensile strength of approximately 950 megapascal and 3 cold drawn conditions up to 75% of cold reduction with a tensile strength up to 1350 megapascal. And the grain size and the lamellar spacing are decreasing with increasing degree of cold deformation. So the strength mechanism comes a lot from the lamellar spacing and from the grain size according to the hole patch. And what's the scientific question now? How does the cold drawing change the hydrogen-induced stress corrosion cracking resistance? And how much hydrogen can every condition resist of these 4 conditions? So we have to find more or less a value, a critical hydrogen content to say, okay, we can use this material under specific conditions or is it not possible? And then, last but not least, also there is the question, why is one condition better than the other? And for the experimental part and the theoretical background, we used to simulate hydrogen diffusion profiles. So solving the second fixed law by a numerical method, we get these hydrogen diffusion profiles we have already seen in the second presentation. And what you need for these hydrogen diffusion profiles is the effective diffusion coefficient and the surface hydrogen content, or the total hydrogen content. And the time of experiment I can choose. And then you can do slow strain rate tests, look at the fracture surface of the charged condition, and you get a brittle behavior where there are when there are higher hydrogen contents, and you get a ductile behavior of the tensile sample in the center of the sample where no hydrogen is. And with these lengths of embrittlement, you can therefore go up to this simulated diffusion profile and determine the critical hydrogen content. So, as the first part, I show the results for hydrogen charging tests. With hydrogen charging over different times, I can measure the total hydrogen content, and with the fitting of this of the solution of the second fixed law, I can calculate the effective diffusion coefficient, and also I can calculate the surface hydrogen content, which is equal to the saturation level of the hydrogen content. And what is good for the carbon steels, I have a faster diffusion, so I can easily get into this saturated state after hours and not after days or months. And as a result, the effective diffusion coefficient is approximately 10 times faster for the hot roll condition compared to the cold drawn conditions. So after these experiments, we have first 2 parameters, the effective diffusion coefficient and the surface hydrogen content. And the length of embrittlement, as mentioned before, we get out from these fractographic images. In the center of the sample, I have a ductile area with dimples, and on the outside of the tensile specimen, I get hydrogen-induced stress corrosion cracks, and so I can distinguish between these 2 areas and measure these lengths of embrittlement. And we did that for all materials condition to get this this last value, the length of embrittlement. But you have to keep in mind here at this point, the length of embrittlement itself is not a parameter for hydrogen-induced stress corrosion cracking resistance, because this value is still dependent on the time of the experiment and the diffusion coefficient, and also of the hydrogen content. So when we put all this together, we get the diffusion profiles. Here for the hot rolled condition, you can see the hydrogen uptake is quite low, but the diffusion is quite fast compared to the cold rolled conditions, and so there's a lot of hydrogen already inside in the center of the tensile specimen. And comparable to 75% cold rolled condition has a higher hydrogen uptake, but slower diffusion. And then we get here with the length of embrittlement values from the RCM images, we get then this critical hydrogen content. And what is interesting, the critical hydrogen content rises here with a higher degree of cold deformation. So the hot rolled condition only can resist approximately 1 ppm of hydrogen, and the material with the highest strength and the highest degree of cold deformation can resist above 4 ppm of hydrogen. But here you also have to keep in mind that also the hydrogen uptake is important. And when we compare the critical hydrogen content with the values which are conventionally performed, or the experiments which are conventionally performed, here the elongation to fracture ratio, so just the comparison of the elongation in air to the elongation in the hydrogen charged condition, then we see again this behavior that the material gets better with a higher degree of cold deformation. So that's quite an unconventional behavior, that the material at the higher strength has a better resistance against hydrogen embrittlement. And so we performed thermal desorption spectroscopy measurements, and in the thermal desorption spectroscopy measurements we see now for the hot roll condition we only have one hydrogen peak at lower temperatures. So all the hydrogen is trapped reversibly and contributes to the embrittlement of the material. While at higher degrees of cold deformation, 20, 50, 75, you get another low temperature peak, but you also got a lot of hydrogen trapped irreversibly in the material at stronger traps, and this hydrogen cannot contribute to the embrittlement. And therefore, the material can trap more hydrogen in the irreversibly trapped peaks or traps, and that's the reason why the material gets better with a higher degree of cold deformation. And we also can show here where is the hydrogen located in the material. We made the thermal desorption spectroscopy measurements at 3 different heating rates, and after solving the Kissinger equation and plotting the famous Joule plot, then we get the activation energy for all our traps and can compare with the literature data where is the hydrogen located in the material. And so the first peak of hydrogen, which is present in all conditions, are the ferrite, perlite, cementite phase boundaries. And the second peak, which comes at higher degrees of cold deformation, are the dislocations in the ferrite phase. And it fits also well together with the dislocation density we measured by XRD. And the last 2 peaks, the high temperature peaks, this is hydrogen, which is located in the cementite phase, in dislocations, and in vacancies in the cementite phase and around the cementite phase. And the cementite phase is only deformed at higher degrees of cold deformation. But then the hydrogen is there strongly trapped and cannot contribute to the embrittlement. So, for the conclusions, the cold rolling in ferrite steel wires improves the hydrogen-induced stress corrosion cracking resistance. So that's the unusual behavior. We have a higher strength, but we have a better resistance. And that is really one point I want to give everyone to keep in mind. that it does not only depend on the strength if a material is good resistant or bad resistant against hydrogen embrittlement. It depends more on the microstructure and also on the strength in the mechanism. And yeah, we have shown here that the critical hydrogen content rises up to 4 ppm for the cold room condition, and increasing amounts of this hydrogen is strongly trapped for the cold deformed conditions at trap sites which are irreversible. So thank you for your attention, and please, if you have any questions.
Thank you very much for the presentation. Time for one question.
Yeah.
Are there, you mentioned some traps,
Yeah.
right? Are they associated to any specific temperature?
Yeah. It is the case here that you measure the peak temperature of every peak, and with this parameter then you can assign every temperature to a trapping site. And you have to do it with literature and also to perform other experiments we did for dislocation density, and then you can put every temperature here to a trapping site. Yeah.
Because we have a background on aluminium, not on steels, and its heating rate is extremely high for aluminium, but it's okay, 200 K per hour?
200 Kelvin per hour. Yeah, for in literature also the heating rates are probably 200, 400, 800, 1200 Kelvin per hour for carbon steels. Yeah.
Okay. For aluminum alloy is 10 degrees Celsius per hour, something like this.
Is it per minute?
Yeah, probably per minute.
Yeah. Okay.
Thank you very much for the presentation.